Now we want to talk about transformations when we change something inside the sine or the cosine function. These changes are going to affect the x direction of the graph. Now these are a little trickier to deal with because we have to apply these changes before we find the sine value. So let's think about an example where I have a little graph, a little function, y equals x squared. If I want to find points on the graph, it's very easy just to pick different values for x and find y. So x squared is 1. If I put in 2, I would get x 2 squared, which is 4. If I put in -3, I would get -3 squared, which is +9, and so forth. But let's think about another function. What if I had the function y equals the square root of x? Well, if I'm going to pick values for x to find y, I'm going to be a little more careful in what I pick. I want to pick values of x that will give me nice, easy to graph y values. So I'm not going to just put any old number in there. I'm going to pick values that are perfect squares, like the square root of 1 is 1, or the square root of 4 is 2, or the square root of 9 is 3. I'm not going to pick 5 and put in there because the square root of 5 is not going to give me a nice number to graph for y. So the same thing happens here. When I am dealing with something inside the function here, I have to be careful to pick values of x that are going to give me nice values of y. So here are my nice points. When I put 0 in for 0 degrees in, I get 0. This gives me the nice point, 0 degrees, 0. When I put 90 degrees, I get the nice point, 91. When I put in 180, then I get 180, 0, 270, -1, and 360, 0. So my nice y values that I want are these nice values. I want to get 0, 1, 0, -1, or 0 for my y values. But I can't just put 0 in for x now. If I put 0 in for x, I would get sine of 0 minus 60 degrees. I would get sine of -60. Sine of -60 would not give me 0. What I want to do is pick a value of x that would give me 0 for y. In other words, I need for x minus 60 to equal 0 degrees so that I get 0 degrees for y. So I need x to be equal to 60 degrees. Because if I put 60 degrees in this function, I would have sine of 60 minus 60, which is sine of 0 degrees, which would give me 0. So my point, instead of being 0 degrees 0, now with my new function, it's 60 degrees 0, which is the point right here. So this point has moved over to here. Oops. Sometimes I hit that button with my hand and an inadvertent window pops up. Okay, in my next point now, I want the argument of the function. I want the value of this angle inside the function to equal 90. So in other words, I want x minus 60 to equal 90. So what does x need to be? Well, x needs to be 90 plus 60, or 150. So if x is equal to 150, 150 minus 60 is 90, and then my y value would be 1. So 150, 1. So this point here moves over also 60 degrees. Because I have to have a number that is 60 degrees bigger than what it was before, since I'm subtracting 60 before I even start applying the sine function. I have to start with a number that is 60 bigger to get the same value, the same sine value as I got before with 90. Okay, so now the third one, I need x minus 60 to equal 180. Well, so now I have x would have to be 180 plus 60, or 240. So if I put 240 in for x, I'll get sine of 180, which is 0. And so 240, 0. So this point is also moved over 60 degrees. My next one, I need x minus 60 to equal 270. because I want what's inside the function to equal 270. So x is going to have to be 60 plus 270, which is 330. So my y value is -1. So I have 330, -1. Notice once again, 60 to the right of where it was before. The last one I need x minus 60 to equal 360. So x has to equal 420, or 360 plus x, in order to get 0 for y. So 420, 0, which is also shifted over from where it used to be. So here's what my graph looks like now. The entire graph has shifted 60 degrees to the right. This is a change in phase displacement. So the phase displacement, I got interrupted there. Back to my original sentence here. My phase displacement is now 60. Remember that the phase displacement is the starting x value of a cycle. So the phase displacement is x equal 60 degrees now. So notice here that when I subtract 60 inside the function, and when I say inside the function, inside these parentheses here, in other words, I'm subtracting 60 before I apply the sine function, the graph shifts 60 degrees in the positive direction. So I subtract 60, but the graph shifts to the right. So it moves right 60, which is the opposite of what you might expect. When if we would subtract outside the function, the whole graph would shift down. But now we're subtracting inside the function, and instead of shifting to the left in the negative direction, it shifts to the right. Because all my x values have to be 60 degrees bigger than what they were before, so that when I subtract 60, I end up with those same nice angles that I wanted, that I had to give me the nice y values. The last one we're going to look at is when we multiply inside the function. So once again, I'm going to write down my nice points that I'm looking for. 0 degrees 0, 90 degrees 1, 180 degrees -1, or sorry, 0. Oops, half point for me. 270 degrees -1, and 360 degrees 0. Now here I want 2x to equal 0 degrees. Well, I can still put in 0 for x. So this point didn't change any. I still have the point 0 degrees 0. Now I want 2x to equal 90 degrees. Because sine of 2x, I want sine of 2x to equal 1. So I need 2x to equal 90. So x would have to equal 45 degrees, so that y would be 1. So now my point is at 45 degrees 1. So here's 1 right here. So it's at 45 degrees 1. Now I need 2x to equal 180. So I need x to equal 90. So when I put 90 into this function, I have sine of 2 times 90, which is sine of 180, which is 0. So my point 90, 0 is on the graph. And I'm going to keep going in the same manner. Here I need 2x to equal 270, so x is going to be 135, so that I get -1 for y. 135 would be right here, and -1. And then last, I need 2x to equal 360, so x would have to be 180 for me to get 0. So here's the last point of the cycle. So here's my entire cycle. We've already gone through changes that affect sinusoidal axis, amplitude, and phase displacement. So this final change affects the period of the graph. The period of the graph now, instead of being 360, the period of the graph is just 180 degrees. It's half as big as it was. If I were to draw another cycle of the graph, it would look like this. There's another cycle. So there are 2 complete cycles in 360 instead of 1. If I complete the graph going backwards, there's another cycle, and here's a final cycle of the graph. So now I have 4 complete cycles of the graph where there used to be 2. So what does this 2 tell me about the graph right here? If I multiply by 2 inside the function, the period equals 360 divided by 2, which is 180, half as wide as before. So if you think about what happens with things inside the function versus things outside the function, what we notice is that changes that happen inside the function have the opposite effect as changes outside the function. Changes inside the function have the opposite effect as changes outside the function. If we had a change outside the function where we added a number, it would make the graph go up in the positive direction. Here, where we subtracted inside the function, we went to the right in the positive direction. So subtraction makes us move in the positive direction inside the function, whereas addition makes us move in the positive direction outside the function. When we multiplied outside the function, the graph got taller, but when we multiply inside the function, the graph becomes narrower, not wider than it was before. The period decreases. So changes inside the function have the opposite effect as changes outside the function, just a little bit trickier. In the next video, then, we'll summarize all of the changes that we see both inside and outside the function.